State, I was working as an instructor at Istanbul Bilgi University. So coming to Penn State, I started Format Lab, which is Form and Matter Lab. And what we do in my lab is to integrate, explore the integration of form and matter and fabrication and performance in the design process by using digital tools and technologies. So these are my current team, but basically most of the work that I'll show today is the work of my students and our collaborative work with my students and our interdisciplinary partners. So over the years, we worked with different types of fabrication technologies and different types of materials, but there are currently two main research lines in the lab, and one is on biomaterials and specifically fungal biomaterials, and the other one is on adaptive robotic fabrication. So very quickly, biomaterials, mycelium. So what is mycelium? Mycelium is the fungal roots of the fungi. And as mycelium colonizes different organic substrates, it binds them. And when you seize the growth, you end up obtaining a lightweight material that has interesting properties for architects. So why are we interested in this? Because current materials that we use in our buildings are not sustainable, and they contribute to about 11% of the global CO2 emissions. Construction industry contributes to around 40% in general, and 11% of this comes from the building materials and construction. So we're exploring a different way of approaching the materials in which we use natural resources, and then at the end of their life cycle, they don't produce any landfill waste, but they just, the right-hand side graphic, they just become part of the nature again, that we could reuse them in the future. Okay, and so I'm going to skip a little bit. As I said, the mycelium is the root part, not the mushroom, and that's where we, and generate our materials. So far, they've been explored in very different applications in design and architecture, from furniture design to more artistic explorations to packaging and myco-leather too. What we do in my lab is we have explored their use as structural materials. So we explored how they could bear load and built this prototype or demonstrator back in 2022, exhibited at University of Virginia. We explore how we can 3D print to eliminate any formwork waste. We explore their acoustic properties. We also collaborated with other faculty in our department to explore how we can integrate mycelium with natural yarns in a project called MycoKnit. So I'm just skipping some slides to make some space for the other presenters as well. But I want to show one project that is still ongoing, in which, so this shows a step-by-step 3D printed, not step-by-step, a 3D printed component using cardboard waste as its substrate, and white is the mycelium colonizing the cardboard waste, and you could see that over time, it colonizes and binds the mycelium, binds the 3D prints. So we're exploring how we could 3D print that using a robotic arm. A robotic arm is these machines that you would see in the past in factories to do repetitive tasks, but in the past 20 years or so, architects are also showing interest in robotic arms to do custom operations. And we developed this extruder attached to the robotic arm to 3D print mycelium-based composites. And in this research, we 3D printed acoustic panels, and we developed a new, I would say, hybrid slicing methodology to 3D print these non-planar surfaces that perform good acoustically. And here, as you could see, one of the panels right after it's been printed and after it's been grown. So another research line, like I said, is on adaptive robotic fabrication. So we integrate sensors to the robotic arm to be able to visualize and capture what's happening around the robot, around the fabrication tools, because otherwise they don't know what's happening. You need to tell them and you need to pre-program them. So, and that we do that through vision-based sensing. So integrating 3D scanners into the robots to accurately represent their environment. This is a project in which we integrated that scanner to the 3D printed panel to capture the changes in the printed form right after it's printed, after it's grown, after it's dried, and after it's oven dried to capture how much the form changes over time. And here's the final grown panel. Okay, one last thing that we do that I want to show is we're also recently interested in exploring how we can collaborate with the mushroom farms in Pennsylvania, because Pennsylvania is the biggest mushroom grower in the United States. It produces 2/3 of the US mushrooms. And the Penn State Mushroom Research Center specifically already had strong ties with mushroom farms in PA. So we're looking into how we could use the waste of mushroom farming, which is the colonized substrates, which they call spent mushroom substrate, to make biomaterials. So we could both get the food and the biomaterials at the same time. So in this case, these are delicious oyster mushrooms that we grew, and then made the biomaterials of. So what's next? We are interested in exploring co-culturing, so not just fungi, but in integrating fungi with other living organisms to enable other properties. We're interested in exploring ways to scale this up. We're interested in reducing the waste of the process. And also through co-cultures, we want to see if we can actually get to negative carbon emissions with our materials. And there's still a lot that is unknown about their durability and their biodegradation. So we want to test those too. And then we want to also compare and explore how these materials, these are novel biomaterials, can meet the requirements of actual buildings. Okay, so this, I think I'm good with time, but thank you. And this is our website and my email.
So as I said, I'm Steve Schmelly. I'm an assistant professor of agricultural and biological engineering, and I'm interested in 3D printing, both with lignin and with cellulose, to make nanocomposites for structural applications. A little background about me. My last name Schmelly actually comes from the Czech word for hops, so it's maybe appropriate that I'm in agricultural and biological engineering because, as I understand it, the Schmelly is the hops farmer. Actually have a PhD in synthetic inorganic chemistry from Vanderbilt University. So kind of took a left turn after doing some research at the National Renewable Energy Lab, which is a U.S. Department of Energy research lab in Colorado, related to biomass valorization, making useful things from plant matter to support the production of liquid fuels that are renewable and sustainable. So I hail from Nashville, Tennessee, which, if you're familiar with country music at all, it's the home of country music. Nashville is Music City, USA. Actually, the arrow there is pointing at a building that I lived in when I was in graduate school that no longer exists. Thus is time marches on, I guess, and the city has grown quite a lot. That's actually the location of a Four Seasons hotel, so I probably couldn't even afford to stay one night in my old stomping ground in Nashville. But of course, we've got guitars that have names and hot fish and chicken and barbecue. It's all wonderful. So love to talk about all the great food that's in Nashville. So as I said, my training is synthetic chemistry. So we're interested in how we can modify both lignin and cellulose to create resins for 3D printing by vat polymerization. And if you think about lignocellulosic biomass, with apologies to Professor Anderson, the biologist that I know of in the room anyway, you can consider plant cell walls as nature's composite material. We'll just completely ignore all the living stuff that's in there and say, if you think about plant cell walls, they kind of function a lot like rebar reinforced concrete, where the cellulose is sort of like the rebar and the lignin is kind of like the cement that glues everything together. And so in my lab, we're interested in doing chemical modifications to that lignin. We see essentially three major things about lignin that are important. Number one is that they have lots of hydroxyl groups whose presence or absence we can control with chemistry, and therefore then do chemical reactions at those sites to make the lignin amenable for polymerization, for example. They also have sites with high absorption cross-section, especially for UV photons, which is starting to sound like something that would work really well in vat polymerization techniques that use light to create solid objects from resinous materials. And finally, if you've worked at all with lignin or have know anybody that is a glutton for punishment, you have probably heard the saying that you can make anything from lignin except money. So people have been studying lignin for a long time, and the major issue is that lignin is a mixture of useful chemicals, and you have to use a lot of unit operations to get to singular things that you can then upgrade in the way that we do petrochemical refining currently. Instead, in my lab, we like to think of lignin as a useful mixture of chemicals. And the fact that it is a mixture, then we leverage to do interesting things. So we don't worry about unit operations to separate it into individual components. We just use it as a mixture of stuff. And as I mentioned, we 3D print by vat polymerization. One type of vat polymerization is called stereolithography, you may have heard of. There's also DLP printing. And then basically what you're doing is shining light on these resins that contain molecules that can absorb that light of a particular wavelength. In this case, it's about 405 nanometers. And those molecules then become active and they initiate a polymerization process. And this all happens in a matter of seconds. So you can essentially print very small volume containers that we call voxels, which are analogous to pixels in a 2D image. And so we get really great resolution, especially by vat polymerization, because just like an image is higher resolution the smaller your pixels are, your 3D printed object will have higher resolution the smaller the voxels are. And so printing with light is really good for making high resolution objects. Of course, lots of things you can do with photopolymers, especially ones that contain lignin, could be useful for wood products, cosmetics, and dental fillings. As I mentioned, we're really interested in construction materials, especially really large format 3D printing. And here's just a quick little video of what's going on. But you can see this is sped up, but that object sort of grows from nothing, from a liquid bath, an actual object comes out. And so as I said, we've been doing this with lignin. You can see in the bottom right-hand corner, that's actually one of the lignin-containing resins that we make. And we've gotten pretty good at making these nice and homogeneous. When we started this research years ago, we literally would purchase resins from Amazon and try to add lignin to them and then characterize their properties. And then what we realized is that there's actually a lot of engineering that's involved in making these resins because they are mixtures and each component in the mixture has a really specific purpose. And not only that, but if you don't do anything to the lignin, they're not particularly miscible. You can't really dissolve lignin in resins in that way. So we found this open source resin that you see on the bottom left-hand corner. And we can create resins that look like that. And ultimately, our hope is that we can create resin materials that actually don't contain any petrochemicals. We really believe that lignin can do all of the heavy lifting, be it as the oligomers or the cross-linking agents or even the photoinitiators in those resins. But here's an example. We can print with poplar lignin. Certainly hardwoods are a big business in Pennsylvania. The name of the state that we live in, Pennsylvania, literally means Penn's woods. Hardwood wood products industry is very big in the state of Pennsylvania. But as you see, as we incorporate lignin into objects that we print, we get really nice surface morphology. We get really clear things that are actually printed. Maybe you can see the graph paper that's behind even the darkest brown material, you can still see through it. So we don't get a lot of defects. And maybe perhaps most importantly, we actually get a really big increase in some mechanical properties like tensile strength, Young's modulus. We've found that we can tune this even more by incorporating nanocellulose, which I don't have any information in these slides, but essentially go back to the drawing board with our lignin-containing resins and then incorporate nanocellulose like cellulose nanofibrils and get a huge increase in mechanical properties in that way too. So we're really focused on how can we build those nano-interfacial interactions to really get the most enhancement in these composite materials. So here again, here's that you can make anything from lignin except money. We really can control molecular weight distributions. We can control hydroxyl group content. We can control photon absorptivity, all the things that we need to do to make really good resins. And ultimately, as I said, because we think of lignin as a useful mixture of chemicals as opposed to a mixture of useful chemicals. Um, a lot of polymer scientists sort of cringe at this, right? Because we're really used to, as polymer scientists, having, for example, ethylene, really high purity, and polymerizing that into polyethylene. Um, we're not used to working with mixtures of things. In fact, when I bring those brown resins over to somebody and say, "Hey, can I borrow your GPC?" they really hesitate, right? You don't want somebody squirting brown stuff into your $100,000 instrument. But we do this already in other fields. Like jet fuel is a mixture of chemicals, and we don't think of the individual components in jet fuel having utility. It's the fact that they're mixed together and they have, as a mixture, a set of performance properties is really a useful way to think about what we can do with lignin and with cellulose as well. So as I said, we really think that that entire molecular weight distribution of lignin that we isolate from plants could be useful for all the components in a renewable resin. And we're really working towards making 100% renewable materials using lignin and potentially doing very large format 3D printing. This is an image of of an FDM printer at the manufacturing demonstration facility at Oak Ridge National Laboratory. Is actually used to 3D print an automobile. So this is where we're hoping to head towards, is using DLP to print large format things like, for example, a wind energy rotor directly on site, 50 meters long. All you have to do is transport the printer and then you can print it out right on site.
Steve,
So
I don't want
I'm
to
gonna
interrupt. Yeah, maybe
yeah, I'm just
we're
going to end it right
good.
here. Just give
Super.
credit to all the great grad students that work on everything, and really happy to hear what everybody's working on and to meet everybody. So thanks very much.
Thank you very much. And we won't miss a beat, and I'll turn it over to Shanghai.
Yep. Thank you.
Mhm.
Uh, um, I think it's probably great. Good afternoon to everyone in United States, and for us here is it's the morning, as 9 to 11. So can you hear? Can you see my slides? Great. I just quickly swap. Right. My sorry. A little bit introduction about myself. I am a lecturer at the Chemical and Materials Engineering department. I mainly works on the advanced materials for energy storage, particularly for the batteries perspective. And here, it's my great pleasure to share with you what we are doing and to see hopefully we could have some collaborations in near future. A little bit background, since it seems like we have quite broad, you know, researchers from quite broad areas. So the batteries, I think you probably heard a lot in terms of in electric cars or others applications. I think what I want to really quick highlight around here is the current lithium-ion batteries. Definitely the performance is really good. But in terms of the demand, we would want in next 10 years or 20 years, I think they're facing a number of issues, in particularly in terms of like the raw material from the lithium, cobalt, nickel, and all these materials in terms of like geographic limitations and also the amount of flame wood we have as well. And the other perspective is certainly is about the cost perspective is and then and one more thing is the current lithium-ion battery from my point of view is not actually designed for recycling or for the whole sustainability development. So that's probably the main motivations for my current research. So the first, what I want to share with you is we currently working on the magnesium-based batteries, including the primary battery and the secondary battery. The magnesium is one of the thing is that you pretty much we kind of like it's a essential sort of elements to our healthy perspective, and is if you look at the industry application perspective and role really in terms of the industry, I mean the engineering side of the applications. So comparing with it has quite sort of like a number of potentials in terms of the cost perspective, in terms of sustainability, environmental friendly perspective as well. And you probably also find that it's in quite a lot of our dairy foods perspective as well. So from the battery chemistry perspective, actually, from both the gravimetric energy density, I mean, of course, from theoretical perspective, volumetric capacity is comparable with lithium-based batteries. But the main problem is the reaction kinetics. So it's for the magnesium, say primary batteries, like actually it's already commercialized already. I mean, as a reserve battery or um, emergency batteries you put initially, it's like you can deactivate this material and these batteries well after manufacture it, and when you need it, you just assemble it, and pretty much it's quite simple, and you can certainly develop um, provide enough power for example, charging your mobile phones, particularly if there's an earthquake or there's a sort of the any sort of like emergency requirement due to the power outage. Um, and the second part is certainly magnesium ion. It can be charged and discharged. This and of course comparing with like the other sort of lithium ion battery or sodium based batteries, the electrode materials you don't have much options, and including the electrolyte as well. So there's a big development, particularly in this area as well. Move on is just briefly give you a roughly idea what we studied in last few years. So we first came from the anode perspective. The negative electrode, put this way, is that we identified research gaps in terms of like the pure magnesium has most widely studied as the anode material for magnesium ion recharge batteries, and then the lead tin based or bismuth based also being studied, but not much really come from our materials engineering background, like designing different type of sort of alloys with special compositions, and because we know that it could have totally different sort of the structures and or morphologists in terms of secondary phase as well. So that's what we started it from the fundamental electrochemical perspective. And move on. And but for that study, we didn't do much in terms of the electrolyte perspective. And for the metal air batteries, it's the same thing. We also many come up from the anode perspective. Let's just give you rough ideas. It's like what the alloys we develop around here and how the performance looks like, and comparing with the pure magnesium or commercialized magnesium alloys. And then interesting thing is we did a bit more in terms of the using 3D printing to we're just challenging in terms of the cell structure perspective. The batteries will normally you're using like current the pouch cell, for example, for our mobile phones. The reaction area is pretty much is like 1:1 that ratio, and so we challenge that in terms of like if we decrease or increase the reaction area between the anode or the cathode, and what will be happens. The interesting, of course, is still based on our more accessible in terms of the metal air battery cell structure. And so the interesting is then the battery, the performance significantly increased when you actually by controlling the anode to cathode reaction ratios perspective. And these are some of our preliminary results so far. And then the other main area, probably more interesting to the group here, is that so based on our previous research, we currently are starting doing a bit more in terms of converting the New Zealand biomass for the biomaterials, including cellulose, is one of the area we currently looking. It's converting that into biographite or graphized sort of the biomass materials for the lithium-ion batteries or sodium-ion batteries or other sort of the battery performance. These ones is the first study we did, and it's pretty much we converting the New Zealand sludge material with the waste woody materials. This material would collect them directly from the New Zealand east part of New Zealand, which is the whole week regions, and then we converting them, we washing them, and then we did some pre-treatment, and then further is the hydrothermal reactions, and then we able to converting them into the, of course, is the graphite materials. We're able to control sort of the amorphous and the crystalline phase. And then we test it in the supercapacitors, and now we're doing a bit work on the testnet in the lithium-ion based batteries. That's how pretty much the performance looks like after 200 cycles. It still maintains quite good sort of capacities, and that's pretty much from me. Thank you, everyone.
Thank you very much, Shanghai. Appreciate it, and we'll turn it over to Jay.
Great, thank you. So I'm going to talk a little bit about the work that I'm doing with Meng Wang, who's on this call as well, and some collaborators at Auckland. We're basically in the space of biological processes, converting wastes and waste materials into various energy carriers and chemicals. My work more broadly is in environmental biotechnology. So I look at these bioenergy applications, making methane, electricity, hydrogen, other energy carriers. But I also work in nutrient removal and both in engineered systems and also in landscapes. So I share here some streams and agroecosystems. And on the right there, I one of my kind of hobby research areas is in bioprospecting. So going to novel environments, extreme environments, and looking for microbes that can do something better at extreme conditions, like break down cellulose or make methane or get rid of arsenic and things like that. So as Meng mentioned earlier, when we were doing introductions, we were in that initial seed grant group in 2020. The pandemic hit, and a lot of our funds were for student exchange and workshops and things. None of that could physically happen, so we did that virtually. We adapted to it, but I had the privilege of doing a sabbatical in Auckland this past spring, my spring semester, so January through May. In fact, I was the next door neighbor of Hong Yu, who's on the call here. So, so we had an amazing time. Loved it. It was very hard to leave in the beginning of June there. And so this shows the other collaborators, Shang Yi, Felicia Wikiswana, and Weichin Zhuang. And so basically what we're looking at is kind of merging all of our respective expertise areas. So we work in anaerobic digestion, bioelectrochemical systems. I'll talk a little bit about that. And then how do we put all these pieces together? And membranes, I don't do anything with membranes, but Felicia does. And so how do we bring all these things together to get new functionalities that any one of them can't quite do? Anaerobic digestion is basically just using a microbial consortium to break down organic materials, complex organic wastes and residues into primarily methane and carbon dioxide. We call it biogas. And so my group has done work on trying to find novel microbial communities that operate in conditions where a typical system would fail, like low pH. There's lots of anaerobic consortia that love low pH, and they're not in our current engineered systems. And so if we inoculate with them, we can operate at lower pHs. I'm not going to explain all the details of this, but we're still doing a project looking at the digestion of switchgrass, looking across an array of 18 different conditions: temperature, retention time, pH. This is a multi-omic study, so we're looking at metagenomics, metatranscriptomics, metaproteomics, and linking it to the performance of the reactor and which ones break down switchgrass, which ones make methane, which ones make acetate. How can we exploit that information to steer it towards productivity that we're interested in? I don't do any work in this space, but Shang-Yi, who's one of the collaborators, works in chain elongation. So you don't have to come out with methane as the end product. There are microbes that can basically elongate volatile fatty acids to make C5, C6, C8 molecules, which are more energy dense and good for other applications, products and fuels. So bioelectrochemical systems, this is another aspect of what we're working on. It's a lot like what Shanghai just talked about with the batteries, except you have microbial catalysts, whether they're at the anode, breaking down organics or ammonia or some reduced compound, or they're at the cathode, where they're reducing things like oxygen, nitrate, sulfate. Meng and I have a project right now where we're putting in the cathode acid mine drainage and using microbes in the anode to reduce metals at the cathode and recover things. And maybe it integrates with some of what Shanghai just talked about with metals recovery. So basically what we're interested in is putting all these pieces together. And I didn't have a slide on membranes, but we have a membrane expert as well. So and the concept basically is biomimicry. Cows do great, or ruminants do great at breaking down complex lignocellulosic materials and getting lots of the energy out of it in a short retention time. Engineered reactors, traditionally, we run them for 10 days, 30 days, and we don't get great recoveries of resources. And so what can we learn from ruminants that we're not doing in engineered systems? And one of the things is putting these different pieces together. So putting in membranes, putting in electrochemical systems to provide or receive electrons. And so this is a figure of a manuscript that we're working on right now that's basically integrating anaerobic digestion, electrochemically active membranes, and so we can kind of engineer better recovery, better deconstruction. I'm kind of going the opposite direction of what Steve talked about, but deconstruction of these materials and producing energy dense products and fuels. So that is summary of what we've been doing. Thank you for your attention.
Thank you very much, Jay. And I will turn it over to Wen.
Yeah, thank you, Alexandra, and thank you all. Can you hear me? Okay. Good. Okay. Hello, everyone, and good morning from New Zealand. And it's great. My name is Wen Zhang, and I'm from the University of Auckland, and it's great to be here today. And my topic today is about electrochemical surface modification of aluminum by liquid metal for on-site hydrogen generation. And firstly, I will give a brief introduction about myself. And I'm a research fellow and lecturer from the Chemical and Materials Engineering Department, and my background is in designing nanomaterials for high performance supercapacitors and zinc iron batteries. And after I graduated, I started some research on solid state hydrogen storage and applying my electrochemical background on hydrogen generation, which is what I want to talk today. And for my topic today, behind the topic, there is a very simple formula. It's a reaction between aluminum and water to generate hydrogen. However, if we directly throw an aluminum block into water, nothing will happen. That is because there is a passive oxide layer coating on the surface of aluminum. So some researchers found that liquid metal, a gallium-based liquid metal, can be used to etch the passive oxide layer and facilitate the reaction. Because the liquid metal can penetrate along the aluminum grain boundaries. However, there is a huge problem about the surface tension of the liquid metal is very high. That means if we directly drop a tiny amount of liquid metal on the surface of aluminum, we can see it shows like a bow on the surface. That means we only have one point or a tiny contact area between the liquid metal and aluminum. However, if we apply a direct current on the liquid metal, we can see the liquid metal spread out and wet the surface of the aluminum, shows a very low contact angle, and that means a very high contact area. And there is a reaction, the Young's relationship can show the how to reduce the contact angle, like we can tune the interfacial tension gamma 1, 2, 3 to change the reaction between the liquid metal and the aluminum. That process, we call it electrowetting process. And many groups, they are focused on electrowetting process. However, to the best of our knowledge, we're the first time to apply the electrowetting on adjusting the hydrogen generation. Yeah. And there are some preliminary results. If we put the aluminum block in alkaline electrolyte, as the voltage increasing from 2 volt to 10 volt, we can see the contact area become larger and larger. And finally, we can see the corrosive surface of the aluminum after the electrowetting. And after electrowetting and standing in the air for 3 weeks, we can see the liquid metal penetrate from the top surface to the bottom surface. And we also tested the hydrogen generation by use of simple water displacement method. And we can see after the electrowetting, the hydrogen generation with a very fast rate and with a high hydrogen volume. However, without electrowetting, we can see a very slow process and with a low hydrogen volume. Because this project just started a few months ago, and so there are some future research plan. We will explore the electrowetting parameters in neutral and electrolyte or in the air to prevent the interference between the alkaline electrolyte with the aluminum oxide, and then we will also regulate the interfacial tension, gamma 1, 2, 3, and to see their influence on the electrowetting process. And we will also investigate the interlaying mechanisms of electrowetting and the liquid metal penetration pathway. And finally, I want to give a little shout out for our group. We're a big energy material research group, and our research areas involves lithium-ion battery, zinc-ion battery, and black mass recycling in supercapacitors, and hydrogen storage generation, and also metal 3D printing. Yeah, that's all from me today. Thank you all.
Wonderful. Thank you so much. And this time I'll turn it over to Charlie.
Thanks so much, Alexandra. Just bear with me 1 second while I get the PowerPoint thing running. All right, so are people able to see that okay? Great. It's nice to see everybody either this morning or this afternoon. My name is Charlie Anderson. I'm a professor in the biology department here at Penn State, and I also co-chair the Center for Biorenewables at Penn State. So my group studies the dynamics of plant cell walls, and we're interested in the potential uses of cell walls as feedstocks for sustainable bioproducts, and also generating new sources of food from plants. So I'm going to highlight very briefly some research projects that we're working on right now, and we can discuss later if people have questions. So one of the things that we study in terms of trying to understand the dynamics of these complex structures, which Steve introduced briefly earlier, is how the assembly and function of cell walls influences plant growth, development, and physiology. So one of the things that we're interested in, for instance, is how plant cell walls influence the function and development of stomata. Stomata are pores on the surface of plants that can open and close to control the uptake of CO2 and the release of water into the environment. And if we sort of zoom in on these stomatal guard cells a little bit closer, we can see that the pore is flanked by these two kidney-shaped guard cells. And those guard cells, in turn, are surrounded by very strong but flexible cell walls that allow them to elongate and also shrink to open and close the stomatal pore, respectively. So one thing that we understand in terms of how the cell wall is constructed is that the cell wall is made of complex networks of polysaccharides. These include cellulose, hemicelluloses, and pectins. And we try to understand how those elements are put together and assembled into this complex architecture that provides the strength and flexibility not only in these stomatal guard cells, but in other tissues of the plant as well that are growing and developing. So one of our hypotheses as an output of this work is that potentially engineering the cell walls of these stomatal guard cells might enhance their ability to take up CO2 and use water efficiently. The reason being that stomatal opening and closure is a fairly slow process that doesn't match the kinetics of the biochemical reactions of photosynthesis. So by making speedier stomata, we think we can enhance the plant's ability to take up CO2 and convert that into things like plant cell walls that will sequester carbon and provide a useful source of biomaterials and bioenergy. On the sort of biomaterials side, we're interested in how we might generate novel biomaterials from plant cell walls. So again, we're using lignocellulose that Steve introduced earlier, and we're taking inspiration from a group at the University of Maryland here in the US who developed something called superwood. This is wood that is chemically treated and densified, and it increases the strength and toughness of this wood quite substantially. And the hypothesis is that this is done by diminishing the spacing between the so-called microfibers of cellulose, and also potentially moving around some of the other parts of the wood, like the lignin. So a researcher in my lab, Elisa Chernikova, is currently working on a collaborative project to study this densification process at the structural level and compositional level. And one of the basic experiments that we're able to do is we're taking hardwoods that are native to Pennsylvania from 5 different tree species. We're subjecting them to pressure and relatively elevated temperatures for as little as an hour, and we end up with this compressed wood material. The interesting thing is that this material actually has mechanical properties that are equal to or even greater than the structural strength of concrete in some cases, which is kind of surprising and exciting to us. These compression tests have been carried out by Sakib Nasmus, who's a researcher in the lab of 2 collaborators on this project, Enrique and Esther Gomez. So we're doing further analysis of these sort of biodurables materials to see if we can generate sustainable building materials from wood that might last a long time and have mechanical properties that are equal to or superior to that of common building materials like steel and concrete, which also involve a lot of carbon emissions. On the sort of deconstruction side, we're thinking about how we might deconstruct the cell walls of plants more efficiently to generate biofuels and bioproducts. And one project we have going on, this is a collaboration with Will Hancock in biomedical engineering here at Penn State, is imaging the process of cellulose deconstruction at the molecular level. So we can take cellulase enzymes that degrade cellulose, label them with a fluorescent quantum dot or Q dot, and place these fluorescently tagged cellulase enzymes on a cellulose substrate. So the movie that's on the upper right here, you can see the cellulose is in black in the back, and the cellulase enzymes are these white dots. We monitor the binding and motility of these cellulases as they persistently chew along the cellulose backbone. And one of the things that we've discovered is that this process of cellulose degradation is actually inhibited at two ends of the enzyme. So the enzyme has sort of a handle called the carbohydrate binding module, as well as a catalytic domain that contains a tunnel through which the cellulose chain is fed and then deconstructed into cellobiose subunits. Cellobiose can inhibit this cellulase enzyme either at the so-called back door, the exit tunnel, or the front door, the entrance tunnel of this catalytic domain. And we're thinking about how we might engineer these cellulases to avoid some of that inhibition to allow us to more efficiently produce bioenergy and bioproducts from plant cell walls. And then we're also exploring pathways to transform plant cell walls, of which there are substantial amounts on the planet. There's enough wood on the planet, for instance, to feed everybody if we were able to convert the calories in that wood into consumable sugars to feed everybody for about 100 years or so. So we're thinking about how we might process plant biomass, either using chemical pretreatments or even biological pretreatments like growing mushrooms on them. Benay was talking about mushrooms earlier, and that's one of the biological pretreatments that you can subject this lignocellulosic biomass to. Combine this with other technologies to deconstruct that lignocellulose into its component sugars, or feed this biomass to ruminants or pseudo-ruminants, and generate food products that might be useful in emergencies or even global catastrophes. So this is a project that is a highly collaborative project among 12 different researchers here at Penn State. In addition to my group, we're thinking about how we might be able to generate so-called emergency foods and provide food resilience to the planet in case there are events that would inhibit conventional agricultural productivity. So I'm just going to finish up there by thanking the members of my group. We have many collaborators here at Penn State. We're obviously interested in potential collaborations with the University of Auckland, and I'll thank these people for funding, and thank you for listening.
Thank you, Charlie. And I'm sorry if I don't want to mispronounce your name. Is it Mede? I think you are still there.
Yeah, I'm mute. Hi, yeah, this is Miley.
Thank you very much. I'll turn it over to you.
Yeah, just let me share my screen. Which one's over? Can you see that? Can you see my screen?
Yes, we can. Thank you.
Is that PowerPoint? Can you see the PowerPoint?
Yes.
Yes, good. Hi, everyone. Greeting from Auckland. My name is Miley. I'm a senior lecturer at the Department of Engineering Science and Biomedical Engineering. I'm so glad to be here. Just a little bit introduction about my research area. My research is at the intersection of several things. Those fields are computational modeling, additive manufacturing, or 3D printing, material engineering, and biological systems. At the intersection of these four fields, my research and I create. I just mentioned top three, my research area, which is 3D printed materials and multi-scale computational modeling of those materials.
Maybe I just wanted to say that I'm not sure I'm the only one, but your voice is breaking up a little bit.
Yeah, that's correct for us also.
I'm
now it's
not
good.
sure what's the problem.
Well, it's a little back and forth.
But I can see that I can see that some of you are on freeze, but the voice is good. Maybe I can just, I don't know. I can turn off the video and increase the speed of the internet. I'm at the university. Yeah,
Maybe
internet
a
just,
good idea. Yes, how about we try that?
yeah, better.
We think so.
Yeah, I think it is better now.
Yeah, and yeah, this is just two of my previous research projects related to bio-inspired materials. We developed a 3D printed biomimetic hard and soft polymer that is 3D printed, and we can tune the stiffness. And recently, through a fruitful collaboration, is a national project, we developed the cellulose by polyester foam lattices. And as a 3D printer modeler, I was in charge of the manufacturing the 3D printer facilities, and also modeling the defect and imperfections of this cellulose by polyester. And now I'm going to just focus on one of my current research. Any of you has experienced some pain and soreness experience on the bottom of the feet during walking or hiking? If yes, you are not alone. Many people face this issue due to the developed peak plantar pressure that is extended during physical activities. And this problem is worse for people with food-related complications like diabetic people. Up to 34% of diabetes developed at least one foot ulcer during their lifetime. And 85% of foot amputation is related to ulcer. This is a huge problem. But the solution is that podiatrists prescribe insole for those people. But the problem is that those insoles are prescribed by a static pressure measurement. It means that the patients are standing on the specific gate, a specific mat, pressure map, and the podiatrist measure the static pressure and then design and manufacture the insole for them. This is a traditional insole manufacturing, the negative and positive molding, casting, but the current innovative manufacturing is using the 3D printing to scan the foot. Then we have the foot geometry, and then we can manufacture 3D printed insole. But the problem is, as I mentioned, all these insole is based on the static pressure measurement. But we know that our gait, our movement, walking pattern is different while we are moving, while we are walking or hiking or running, and we need to use tools like pressure map to create our insole. At the core of this research is introducing a novel solid liquid 3D printed structures. We can 3D print a specific porous structure and then inject those porous structure with viscous liquid, can be hydrogel, can be liquid metal, and then we can manufacture what we call SLC or solid liquid composite. We can change the geometry of this porous structure with change the geometry, change the porosity to tune the stiffness. And you can see that the left-hand side is a grid. It means that all the part of the insole is manufactured by one geometry, a specific geometry. It means that you can only have one stiffness, but with the machine learning and optimization that we develop in this project, we can have a tunable, varied stiffness through the insole. For example, if you have a peak plantar pressure at the toe area, we need less stiff material, or at the heel, we can have high stiff material. It's an automated, patient-centric approach that we developed to have a customized solid liquid composite. This is the procedure. We have the foot geometry from the scan, and from the MRI, we have the geometry of the bone. And then with the optimization algorithm and computational modeling, we assign at which area of the bottom of the foot, which porosity can be allocated. And then we manufacture by 3D SLA 3D printer, and You can see that, and then after 3D printing, we inject the fluid inside that. The fluid improve the cushioning through the testing, and this is the final prototype. And then we can measure the plantar pressure by this wireless pressure sensor. At the next step, we are seeking for collaboration of integrating the kind of bio-based material like a hydrogel as a fluid, because currently we are using oil, but under cyclic fatigue test, oil is not actually is not working. The insole burst, and we are thinking of to employ hydrogel, because hydrogel has a high fatigue resistance, and how much it can integrate with this porous structure is our next research question. This is my team, Mark, Matthew, and Justin, biomechanics and modeling scientists, and Dana and Shiva, students working on this project. Thank you.
Thank you very much. Exciting, might be very useful too. I can see that already. And our last presenter is Rahman.
Right. Hello, everyone. My name is Rahman Azari. I'm an associate professor of architecture at Penn State. So I'm going to share my screen. All right. Assume everyone is able to see my screen. So I run at Penn State the Resource and Energy Efficiency Lab, RE2 Lab, which is a group of PhD student researchers and faculty focusing on the research on resilient and sustainable built environments. And we do research at 3 scales of building skin, buildings, and cities. And what motivates our research is the fact that a big part of the global carbon dioxide and greenhouse emissions is caused by building what we call operational carbon, which is the carbon because of the energy consumption in buildings. And 10% of that is also about embodied carbon, which is the carbon because of the materiality and construction materials that we use in buildings. So in total, 37% of the global greenhouse gas emissions is because of the buildings. And when we talk about energy consumption in the United States, for example, a big part of the energy use in the United States goes into the building sector as well. And when we look at it at a larger scale, it's not just because of the buildings, but because of the interrelations between many factors that affect the carbon emissions and energy use of the buildings. So these factors could range from policy-related factors to demographic factors to urban physical and eventually the building-related factors as well. So we do research under 3 themes. One theme is about innovative building skins for energy harvesting and storage. And when I say building skin, I mean the wall and the roof and the windows that we use in buildings. So my group is interested in how we could integrate all of these different technologies and solutions for energy harvesting and storage and integrate it into building skin and address all of the complexities around them. For example, Jingshi Zhang, my PhD student, is working on building skins that integrate electrochemical energy harvesting as part of the building skin. And we have all sorts of challenges in that integration that Jingshi is trying to solve. In another project, we received funding to integrate thermoelectric energy harvesting and storage as part of the building skin. So we're collaborating with University of Freiburg in this project, and we're trying to integrate, basically create building skins that integrate thermoelectric energy generators and phase change materials in order to generate enough energy to operate the shading systems in buildings. The second theme of my research is about multidimensional and multiscalar assessment of the impacts of buildings on the environment, society, and health. Basically, in this project, in this area of research, we are interested in what ways buildings and the construction materials that are used in buildings affect the environment in various categories of the impacts on the environment, how they impact social aspects of the life and how they impact the health of the occupants in buildings. So we're trying to integrate various methodologies, including life cycle assessment, energy simulation, and social and health impact assessment in order to reduce the environment, in order to first create an integrative and holistic framework to assess the impacts of buildings and construction materials on environment, health, and on the society in general, and assess those and create metrics to communicate those impacts. The third area of research that I'm involved in is urban energy and environmental modeling, which is about how we could assess the effects of climate change on urban environments and the effects of urban environments on climate change. So how we could develop better understanding of this vicious cycle of the relationship between climate change and urban environments by considering the interrelations of not only buildings and the environment, but also how the occupants, how urban residents are involved in that process as well. One project is Baltimore Social Environmental Collaborative Project. This is a $25 million project that is funded by U.S. Department of Energy. It's the large group of faculty and researchers involved in this research, and Penn State is one of the institutions involved in this project. And this project, we are trying to understand the effects of buildings and energy on the climate change and how we could develop decision science in order to develop adaptation pathways to address climate change. In another project, we focus on Manhattan in New York City and developed carbon emission models for urban habitats by trying to develop a more the accurate understanding of the energy consumption and carbon emissions at the larger scale of the city. And the fourth and the last area of my research is about digital twins for enhanced indoor air quality. So my PhD student, Hanin Othman, is developing a robotic multi-sensing systems that would navigate into architectural space and collect a range of indoor air quality data from CO2 to VOC to PM particles. And based on the collected data, the building facades and building skins would be able to react. For example, windows could open through a central system based on the accurate data that would be collected through a multi-sensing robotic system. Thank you very much. And I look forward to opportunities to discuss this research and find areas for collaboration.
Thank you very much, Rahman. And I was remiss in not introducing or having them introduce themselves, our two observers who are on the call, and that would be Hung Yu and Tristan. If you're happy to, maybe you can just quickly introduce yourselves too. And Prakash, I know you have to leave, but if you'd like to as well, that would be great.
Hi, everybody. Sorry, I have to leave because I have to catch a flight. But I'm Prakash Ranjitkar, and I'm from Department of Civil and Environmental Engineering in University of Auckland. My research is mainly about transportation engineering system, and that involve autonomous vehicle, electric vehicle, and also how to make transport system resilient in event of natural disaster. So yeah, I would be interested if there is any interest for collaboration. Yeah, that would be great. And I'm also in the committee for the LYG committee for this event. Yeah.
Thank you so much, Prakash. Safe travels.
Thank you.
Bye-bye.
Have a great discussion. Bye.
Hello, everyone. My name is Hong Yu, currently working as a lecturer at the University of Auckland. And my research is about public-private partnership and also sustainable infrastructure. Currently, I'm doing a research project try to integrate the construction technology into the sustainability assessment for infrastructure projects. And so to achieve an automated sustainability assessment. And I'm very interested to see the Professor Azari's research, and you are also focused on the life cycle assessment for sustainability. I think we can establish some collaborations in the future. Thank you, everyone.
And Tristan, would you like to introduce yourself?
Yes, all right. I'm Tristan. I'm also at the University of Auckland. I'm in the in the Chemical Sciences department. I'm a biochemist and maybe synthetic biologist. So basically, we're interested in studying nature's chemistry and engineering it for all kinds of purposes. One of them being sustainability. So imagine being able to program bacteria to take feedstocks that may come from some of the stuff that some of you are working on, like biomass, and turn that into the various types of molecules that we use in our daily life. We're also interested in more of the basic science of the individual enzymatic steps that are happening along the way.
Thank you. Wonderful. And with this, I will turn it over to Meng and Steve to moderate a discussion. I know Meng also would like to take the opportunity maybe to post something into the chat as an opportunity for students, and maybe I'll let you go ahead and do that.
Okay, thank you. So thank you for the great presentations. I saw many opportunities, although some partner faculty maybe not here, but I saw some opportunities for potential collaborations. So and here we have one NSF project. Maybe I can share the screen. So innovations in graduate education built upon our collaboration with the University of Auckland. So here we can, since the University of Auckland is our partner institute, so that we can support students from the US to conduct 1 to 6 months of research in University of Auckland in the broad areas of food, water, and energy nexus. So it's quite broad. So and the application is relatively simple. So hopefully I can share my screen. And so the application deadline is relatively close, but it's only like the November 20th. And you can find the information here. And the student, we will support the round trip tickets and also the lodging when the students spend the time in at the University of Auckland, and that should be enough to cover their spends in the foreign country. We know that Auckland is kind of expensive, so we hope to reduce the burden and give students the opportunity to doing the research over there, and also for faculty to build collaboration in that area. So students will submit the application, and then next year we also students will register for 1 credit professional development co-design towards sustainability. So we will kind of work with students on some professional development, like the presentation of communication skills, and also like along with the spring semester, we will check the students' progress about their connection with their partner institute host, and then present their final like the plan. Since we don't want the students just waste their time, we want the students to be prepared so that they can travel between May and like the December. So I hope I can share. Sorry. Okay, so now it's so here is just like the brief introduction about how you can apply. You can just simply submit the application here. So students need to submit the application, but they need to discuss with the faculty about their potential the time frame. So at this point, you don't need to. You just need to propose like the what project you work on, or if you don't know, if you want to do the travel and do research over there, don't have a project, so you can propose something that is like related to this area, and then find the potential. We can help to find the potential fit as well. So and then So we will get this outcome very soon. So students can travel next year if you want to build some like a collaboration or collaborative project. So that's kind of additional resources for you to build some collaboration. Thank you.
Thank you. So again, Steve and Meg, maybe if you wouldn't mind coordinating questions and discussion, anything that might come up.
So like I saw like many of the colleagues from University of Auckland did some research in the bioelectrochemical area and the like the battery aspect. So I want to mention that this Penn State also have the battery center. So I'm not sure if you already started establishing the contact, so I can post a few names maybe on the chat so you can look for their information and establish some collaborations. I know at least our department have faculty like working on the battery and both on the material side and also on the bioelectrochemical side, also computational material side for the solar energy. So I can post down names so you can look for. But there are we do have like the battery center in the, I think it's located in the building of the IE, right? In Institute of Environment and Energy and Environment.
That'd be great. That would be great. Yeah, we definitely have currently have some. I mean, I do have one collaboration from Georgia Tech, but not much from. That'd be really good if we do have like we do have a here we have in our chemical material engineering department, including when we pretty much have like about 4 working on the batteries, related to batteries, and one more working on hydrogen. And across the road in the chemistry, I know about 2 of them academic staff was working on the battery perspective as well. Happy to build that network as well. Yeah.
So I think potentially we can also start gathering some information about how many of you have been starting the like the contact with the faculty in the partner institute, and what the other questions, what like the kind of support you want to see from the group. So that will be some open discussion.
I've not started yet contacting the faculty, but I could start contacting right now that I know Hong Yu is interested in also the sustainability impacts of the buildings. A question that I would have is that what is the process for collaboration? What type of resources would be available to us? What are the timelines or any additional information that you would be willing to share?
That's a great question. And from a global perspective, it is actually the generosity of the International Office in Auckland that is striving to potentially support up to 10 or 12 researchers, faculty to come and attend this workshop at Penn State. We have not built that yet. We were thinking at this point, maybe after our semester is finished, maybe around the middle of May as a potential, we will add a question into the post-workshop survey. And the idea being that maybe we see our role as facilitators and getting the right people together, and based on the workshop today and as well as tomorrow's, to see where are potentially very good prospects and connections going forward, and then to enable the researchers to have that time together and explore that further. But probably to have some ideas really and identify already a plan to a certain degree as to what to pursue. We do not have money at Penn State, for example, to continue the seed collaboration program at this very moment. That doesn't mean that we won't in the future. So we're trying to support as much as possible, and by making it available to the Auckland researchers this time around to travel to Penn State.
Thank you so much.
Just following that, a little bit information I can share from what I know. First, New Zealand we do have, I mean, from the from the government or the national sort of level perspective, we do have the catalyst fundings, and each year the catalyst funding is pretty much is like if we, for example, we build the research. The funding is for building the research collaborations. So it's funding the travel course and also hosting the seminars as well. And so, but the application is from the research in I mean academics by ourselves. So and we have to write like a proposal. I think I'm not sure when have you applied, but definitely I know Penn applied quite a few. So that's one of the opportunities definitely for us. And in terms of the other research funding, I'm not so sure whether. So I'm not sure whether New Zealand government have allocated particularly sort of the collaboration research grant between New Zealand and United States, but I definitely know that there are special ones for like between New Zealand and Japan, New Zealand and China, but only a few. Like New Zealand and China probably only 3 each year, and New Zealand and Japan is about 2 or 3 as well. I tried once with New Zealand and Korea once. It's like three projects, like 300,000 for 3 years, and I'm pretty sure that there could be some more opportunities come up in near future. And in just the second point I want to share, David, is we do have a energy and research center. So particularly this year, our engineering faculty actually is joining. It's become a new faculty in incorporating the architecture building and the plan as well. So from what you just described, actually, I can share the screen, so I can share the centers, how it looks like. I'm happy to quick introduction about this one. We have that's the green green energy engineering center. So pretty much what you described in terms of your buildings and including the digital twins. Brent Young, as he's from my department as well. He was his former HOD, and actually he's doing quite a lot of digital twin. So we do have a big, similar like your project, it's a big research program funded, I think, about 7 years. But the host is not us. It's not us. It's the University of Waikato, down Hamilton. So they do particularly trying to using the digital twin for improving the energy efficiency in particular in New Zealand industrial perspective. Just give you rough the ideas, and so I'm happy to link with you to the Andy and our directors and deputy directors, Brent, if you do interesting. And the last workshop we had the academic staff from the architecture and planning, and talking about also about the building efficiency, energy efficiency perspective. That's this pretty much a news perspective, and then all the from engineering side, this center is from our faculty of engineering, pretty much who works on the energy related projects are the PIs around here. I'm happy to help with you to build an linkage if you do interested in that. Yeah. And we do have, just give you a rough idea, is that we do have an energy center across the university and with business school as well. And what else? Yeah, I think that's in terms of the I think there will be some good opportunities in terms of if sorry, one thing is about the back to the first point is probably the research grant perspective is the New Zealand do have like the large research program like 10 million for 5 years that thing, and they do focus on particularly must have the international collaborators. I think with your research expertise, certainly is a benefit to the whole team. Yeah. I will put that website link on the chat in the chat.
A quick question: whether the energy policy related to, for example, the grid, or is a part of the
Yes.
center as well? Okay, good.
It's not. We do have the policy perspective is not from our engineering side, but definitely is the university side. We do have like energy. I think the whole energy center is kind of, we do have the university level, and when we also have the whole Auckland regions as well. So yeah.
Thank you. Yeah, it seems the other big areas in the the biomaterial, maybe Steve, or you have some insight or some on this aspect of collaboration, or Charlie.
Yeah, I
Yeah.
certainly think there are some opportunities in biomaterials. Go ahead, Steve.
No, I was just going to say that, Penn State's organizational structure, we have research institutes and centers, and between Charlie and Rahman and me, we represent two of the centers. Charlie mentioned the Center for Biorenewables, and Rahman and I are also part of the Institute for Living Multifunctional Material Systems. We are also members of various colleges on campus, right? So like I in the College of Agricultural Sciences am interested in ag and forestry in general. So definitely lots of things to look into. We didn't mention the Catalysis Center. I don't think there's any other. It's kind of strange that there's no chemical engineers in this group, but the chemical engineering is home to the newly formed and growing Center for Catalysis Science. And I know that electrochemistry is a big research focus at Penn State. And so I'm going to try to find a link and put that in the chat. Excuse me. But there's folks there that I can also help people get in contact with who are interested in electrochemistry, just sort of broadly. There's lots of people at Penn State who are interested in electrochemistry for all sorts of things. So I will definitely, let me find that link and I'll put it in the chat.
Sorry, Steve and Meng, I do have a quick question. Is that in your university, do you have someone working particularly like marine like seawater perspective? It could be like extraction for the minerals, or for the what do you say, like distillation, or the do you have anyone works on that perspective?
Yeah, so Penn State is a Sea Grant school, which is surprising to me, that because Penn State is geographically located in the middle of the state of Pennsylvania, but Pennsylvania actually touches Lake Erie, which is connected to the Atlantic Ocean, and maybe somehow touches the Atlantic Ocean on the eastern side. I'm not even sure. But in any case, the answer to your question is probably yes, qualified yes. I don't know the person, but I could definitely find out who those people are for sure.
Okay, thank you, Steve.
Yeah, somebody named Fei Shi in Earth and Mineral Engineering, Energy and Mineral Engineering, is doing something about lithium extraction from seawater.
Yep.
Yep.
And I know there's a faculty in chemistry, Joey Couture, who's interested in designing proteins for rare earth element extraction from various systems, potentially
yes.
including seawater.
Yep.
And Fei-Fei's contact info is already in the chat there.
Yeah, and also we have the critical mineral center. So if someone is interested in looking that, so you can search online. So there are already some like the potential being palatable technology going there, and also a wide range of stakeholder engagement. So that's another resources.
That's very
And
interesting.
for the desalination part, I think we have the membrane center as well. So that's faculty affiliated with that center also working on some desalination. I think Dr. Bruce Logan also work on some of desalination, right? Jay may also have some.
Yeah, Bruce Logan, Chris Gorski, and also in the hydrogen production area. So maybe Wen is interested in that too. So
Thank you very much,
electrochemistry,
Jay.
desalination, hydrogen production.
So we should also say we've thrown all these names up here, and sometimes it's difficult to just cold email somebody. So now that you've met all of us,
Yeah.
I mean, I think we would all volunteer to say happy to send an email to both of you, and CC each of you, and sort of make that introduction. I think that would be more useful than just saying, "Oh, email this person you've never met before." So maybe we could sort of coordinate how we could introduce people, and I think that would be really helpful. Because I'm not particularly outgoing, so you could tell me 10 people at Auckland and I would be really nervous about just emailing them. But we're here to help you, so we can do that.
Yeah. Same thing, likewise as well. I'm happy to if you do find out any person that in Auckland you're particularly interested, cooperate, and I'm happy to help you as you build the connections.
So I'll go ahead and volunteer to connect you to the folks in the Catalysis Center. I know Bert Chandler, who is the director of that center, very well. So I will email him and CC you. I assume we have everybody's contact info in this, maybe the Word document that was part of the calendar invite. I see Alexandra is shaking her head. Yes, that's good. So I can facilitate at least that connection and get you in contact with folks in the Catalysis Center. And then Bert will have more information about specifically who's I can't remember the folks who are doing like traditional fundamental electrochemistry off the top of my head, but I know there's lots of people who are doing it. So
Yeah,
he'll
Feifei
be a
is
good
working
entree to that. Yeah.
Thank you very
And
much
also,
for that. Thank you.
Yeah, Jay and Hong are all honed in the civil and environmental engineering, so they're also, and maybe potentially connection with the sustainable infrastructure. So Raymond, so you may have some connections already, and then currently it looks like so there's like not too much resources at this point for the Penn State. So I think ours, like the NSF IGE grant, will be a good opportunity to help the Penn State faculty to start some collaboration with the University of Auckland. So we can support 1 to 6 months of research. So you can propose and then because of some, if the travel happened in the semester, so there are also some administrative work we need to do, so we can explain the things. So feel free to contact us if you have any questions. And we have the whole semester, spring semester, to continue polishing the project and refine the students' project, so they can have a immediately start when they start their travel from May to December. That's a time frame for travel.
It would be great if we have some students coming visiting and doing a few months internship in our laboratories. Just curious that is there similar programs that the students from Auckland University they can do also have the exchange internship in Pennsylvania State universities? It's a no.
No, currently since we got the grant from National Science Foundation, so they can only support the US part. And the other opportunity potentially from NSF, there's also a wide kind of identify a site for the international site for the students' kind of education purpose. So that is another potential source for funding for the international collaboration with the University of Auckland.
Gotcha. I mean, it seems like the staff here, we need to do more work to get get more fundings to support our students. So, yeah.
And we also want to know if the Penn State University has any group focused on hydrogen generation or hydrogen storage. Please let us know. We are looking forward for the collaborating with Penn State University. Yeah.
Yeah, there's actually someone in my department, Sibel Ermach, who is interested in generating hydrogen from biomass, but sort of interested in hydrogen generation in general. Some of the people may be in tomorrow's the word just went right out of my head. Yeah, the meeting that's like this, but that's happening tomorrow. There may be some additional folks.
That's right. That would be on the energy side more. That
Yeah.
would be tomorrow's. And yes, there's a chance, Steve.
And I
Yeah.
just to plug, Charlie put in the chat the link to the hydrogen energy research center at Penn State. And again, if there's folks in there, like I don't necessarily know that I know the people off the top of my head, but am happy to play intermediary. So you can send me a note and say, hey, do you know so and so? And I'd be happy to introduce whomever needs to be introduced.
Same here, Steve. Charlie, you beat me by like 2 seconds. But I'm happy to connect anyone with civil and environmental engineering people. And also, I know that Prakash left, but we have people that do autonomous vehicles and traffic routing models and things. So I could connect him with those people too, if he's interested.
Yeah, and the
Hello.
faculty in our department is working on the hydrogen, underground hydrogen storage.
Thank you. Redman said if we have any architectural application for our project currently, we did some basic fundamental science research, but if we got any idea about any architectural application, I will let you know. Thank you.
Are there any other questions, clarifications? We will follow up. Great idea. We'll make sure so that you don't have to Google the email addresses. We'll share with this group all of the email addresses and names. As I mentioned too, we will follow up in a survey to ask more specific questions about your interests in collaborations, and then really we'll take it from there. So we'll have an application process of sorts, but for the Auckland attendees, do think about whether a time frame next year in May might be something where you could entertain a visit here, and it would depend also on collaborators at Penn State, their availability, and not everything has to be obviously on travel. I think the discussion just now about who to connect with whom and doing that virtually is wonderful. So that's a little bit from our perspective, the next steps.
And then when you come visit, make sure you come take part in my college's thing that they love to advertise, which is the Penn State Berkey Creamery. You get all the great ice cream that you could ever want. We have some good ones, so I can't wait for you to come visit. Check it out.
And unfortunately, we'll probably have to make sure it doesn't coincide with the blue and white game, because Penn State University Park here becomes the third largest city in Pennsylvania when we have a football game. Yeah. And it is very difficult to find a single hotel room anywhere nearby. Well, I'd like to thank you all so much again for presenting, for moderating, for coming as observers. This is just the first step, and we hope for really wonderful opportunities going forward, but it wouldn't be possible without you all. And therefore, thank you so much again, and we will be in touch.